So before starting the example, let's go back to the orthogonal decomposition theorem. Okay, so it was the orthogonal decomposition theorem, right? So we proved this one. So if we have the subspace W, right, and orthogonal basis of W here, right, and given arbitrary vector Y in Rn space, it doesn't necessarily mean the Y is in the double space, but Y can be any arbitrary vector in Rn space. Then this vector Y can be represented by Y hat and Z, right? So Y is equal to Y hat plus Z when Y hat is equal to here and Z is equal to here, right? So this is the orthogonal decomposition theorem. So it means that if you go back to the our discussion here, now we have the way to estimate the Y hat with the basis orthogonal basis of the W with the Y hat. Y. Then we can find out Y hat by orthogonal decomposition theorem. Okay, so let's see the example. Before that, if you remember this one, vector Y is in Y W and W perpendicular. So because these two spaces orthogonal each other, so this V, the vector V, inner product vector V is equal to 0, so vector V is equal to 0 vector, right? So I just keep this one, but if you I just wonder, do you understand this one or not? Okay, anyway, so let's go back to the example. Let's say the vector u1 is equal to something like this, right? And vector u is equal to something like this, and we have the vector y here, right? Observe that vector u1 and u2 is an orthogonal basis. An orthogonal basis for w is span u1 and u2. So u1 and u2 is the orthogonal basis for w span u1 and u2, right? So first of all, why this one is the orthogonal basis? Basis is right because the W is the span of U1 and U2. But why this one is orthogonal? Because Y1 inner product Y2 is equal to 0, right? So you can compute this one, but you can easily find out this is orthogonal basis. Okay? So in this case, write Y as the sum of the vector in W and vector orthogonal to W. Okay, so let's say there is the there is U1 and there is U2, and this is the subspace W span U1 and U2, and vector Y is here, right? So in this case, we want to represent the vector Y as the sum of the vector in W space, and vector orthogonal to W. So there is 0 vector. So the problem is to find the Y hat that is perpendicular to orthogonal to W. So this one is Z is equal to minus Y hat. Okay, so the problem is find out Y hat. Okay, so in this case, Y hat is the projected vector of Y onto the subspace W. Okay, so how can we find out the Y hat? by using this representation, right? Okay, let's do that. First of all, we have the y and the orthogonal basis u1 and u2, right? So we can find out the y hat is equal to vector y inner product to u1 over u1 inner product to u1 times u1, right? And plus vector vector y inner product to vector u2 over vector u2 inner product vector u2 times u2. Okay, so what is that? What was the y? So 1, 2, 3, right? What was the u1? What was the u1? 2, 5, negative 1, 2, 5, negative 1. And what was the u1? 2, 5, negative 1, 2, 5, negative 1, and 2, 5, negative 1. So what is that? 2 plus 10 plus negative 3, right? What is that? 4 plus 25 plus 1, right? So in this case, this is the 30, this is the 9. So here, right? And u1 here, right? What about this? What about this? Y is equal to 1, 2, 3, and y2 is equal to negative 2, 1, 1. Negative 2, 1, 1, and negative 2, 1, 1, negative 2, 1, 1 here. So in this case, negative 2 plus 2 plus 3, and 4 plus 1 plus 1 here. So this is 3, and this is 6, right? So here, here, and this is u2, right? Okay. Then the summation of these two terms is equal to negative 2 over 5, 2, and 1 over 5. So you can easily derive this one. So I will just skip this, and yeah, that's it. So y hat is equal to this vector. So and the perpendicular vector z or the orthogonal complement z is equal to y minus y hat. So because y is something like this, y hat is something like this, so y minus y hat is something like this. Okay, so here, if y is 1, 2, 3, y1 is 2, 5, negative 1, y2 is negative 2, 1, 1, then y hat is equal to negative 2 over 5, 2, 1 over 5, right? And z is equal to 7 over 5 over 5, 0, 40 over 5. Okay, so this is the orthogonal projection of the arbitrary vector y onto the subspace W. Okay, so that's it. So orthogonal decomposition theorem ensures that y minus y hat is in W perpendicular space. Y minus y hat or z. This one is in W perpendicular space. So to check the calculation, the verify that the y minus y hat is orthogonal to both u1 and u2. So how can we prove that this one? Y minus y hat is equal to 7050 4005, And what was the u1 and u2? 2, 5, negative 1. 2, 5, negative 1. Negative 2, 1, 1. So you can easily verify y minus y hat times u1 and 7505005 with 2, 5, negative 1 and 530 plus minus 3005 to future, right? So it shows that these two vectors are perpendicular or orthogonal, right? So you can easily verify y minus y hat inner product u2 is equal to 0, right? So because the y minus y hat is orthogonal to u1 and u2, hence this y minus y hat is orthogonal to all of the vector in W space. Okay. So that's it. So the desirable decomposition of the y is equal to y hat plus z. Okay. So y hat was something like this. Z is something like this. Okay. So this is the examples of the orthogonal decomposition theorem. Okay, so let me show the geometric interpretation of the orthogonal projection. Okay, so orthogonal projection of the y is the sum of each projection onto the one-dimensional subspace that are mutually orthogonal. So what does it mean? So let's say there is a vector u1 and vector u2, something like this, right? And here is y here. Then subspace W spanned by u1 and u2, something like this, right? Then we want to find the orthogonal projection of the vector y onto the W space here. So this point, the vector y minus y hat should be orthogonal to every point in the space W, right? So what is the geometric interpretation of this y hat? So in this case, if we can find out y hat 1 and y hat 2, then y hat can be represented by these two terms, summation of these two terms, right? So, and then how can we find the y hat 1? Y hat 1? So y hat 1 is the orthogonal projection of the y onto span of the u1 or the line L spanned by u1, right? So how can I find this one? If you go back to the lecture 9.2, there was also a projection onto the line L, right? So it was something like this, right? Similarly, this y1 hat can be represented by y1, y1, by y1, something like this, right? What about this? Y2, y hat 2 is the orthogonal projection of y onto this line, right? So in other words, y2 hat is equal to y2 inner product y2, y inner product y2, y2, right? So in other words, y hat is equal to y1 hat plus y2 hat. So finally, we can represent y hat as the something like this, right? So in other words, we can easily extend the y hat onto the higher dimensional case rather than two vectors. So anyway, so this is the geometric interpretation in the 3D space. So this one is the definition in orthogonal decomposition theorem here. Okay. Okay. So if the y1 through the yp is the orthogonal basis for w and y happens to be in w, so what does it mean? Okay, if there is a w here spanned by u1 through the up and y happens to be in here, then the projection jwy projection wy is exactly the same of the y here. Why? Because if you go back to the theorem in our lecture 9.2, where is the theorem? Here. This one, in this theorem, the y should be defined in W space, right? So if you have the y in the W space, this definition will be exactly the same to y. Okay, so in this case, orthogonal projection of the y onto the W space is equal to y itself. Okay, so in other words, if y is in W spanned by like this, then projection wy is equal to y itself. Okay, so yeah, in this case, this orthogonal decomposition theorem is exactly the same as this theorem. Okay, so this is a special case of the orthogonal decomposition theorem. Okay, so this is the relationship between today's theorem and the last week's theorem. Okay, so yeah, there is one more theorem. So this theorem will be discussed in today's lecture. So today in today's lecture we will finish here, but if I summarize this lecture, please remember this figure. So So now we can represent the y hat using the given y and the basis of this space w, right? So why we need this one? So now we have the if we have the AS equals B that has no solution, then we can represent the column space of y, column space of the matrix A, right? Called W, and given C, then in this case we can find out C hat similar to the y hat. Then this point, y C hat, will be the nearest point on the column space. Okay, so it means that by using this point, we can find out the approximated solution of the AS equals C. Okay, so this is the end of presentation. Thank you for listening. And finally, please remember that there is a homework 3 until this Thursday. Okay, thank you.